Hello friends, so today we are going to continue with, or rather we can say we are going to solve 3 questions, and these 3 questions are from rotational motion. Okay, and one second. So in the first question we are okay. So in the first question we are given a small solid ball of radius r rolls without slipping inside a large fixed cylinder of radius r, capital R. The ball stays near the bottom and makes a small back and forth oscillations. What is the frequency of these small oscillations? Assume the ball is much smaller than the cylinder. It means small r is very much lesser than the capital R with respect to their radius. So this is our first question. And so here we are given that the solid ball is rolling and it is doing without slipping. And so we can just draw an approximate figure, and the larger cylinder is fixed and that is having a radius of capital R. So suppose we are having a larger cylinder and this is the center and the lowest point is suppose given as point P, and in this we are having a smaller cylinder and the radius of this smaller cylinder is given as small r, and we assume that it moves by a small angle, and that angle is, let us suppose we call this as a mu. Okay. And therefore we can say that so we are having the radius of this bigger cylinder is given as capital R and the radius of the smaller cylinder is given as small r. So it means the center of this smaller cylinder will be at a distance of r minus small r. But here we are going to use the approximation that is given to us, that is, so we can say that our the ball is inside the cylinder and its center is at a distance, and that distance is capital R minus small r from the cylinder's center. From cylinder's center. But we are given that this small r is very much less than the capital R. Therefore, we can write that our r minus small r will be approximately equal to capital R. So which means that the center of the ball is going to move with a radius of capital R inside the cylinder. Therefore, from here we can draw a conclusion that the ball center moves along a circle of radius capital R. And so now let us, in the extreme position when the angle is mu, let us call this extreme position as P prime. And at this point P prime, so we can see at P prime, we can easily find out the forces that will be acting on it. So we have this is a part of the cylinder, and the small ball is at a point P prime. So obviously we are going to have a mg and in the downward direction, and which we can divide into two components. So this will be our mu that we have taken as angle. So we are going to have our mg and cos of mu, and toward the mean position we are going to have this as mg sine of mu. Okay. So this is the component of the mass which is basically going to act as a restoring force on this ball. And therefore, and this is, so you can see at P prime, the component acting as restoring force will be our mg sine of mu, and restoring force we can add a sign of negative to it. And it is also given in the question that is the rolling without slipping, so obviously friction force will be present there, and therefore we can write that our friction it is basically going to oppose our slipping, but it is going to help in the rolling. So you can friction, from here we can say rolling without slipping. Helps rolling without slipping. Okay. And therefore the friction will be acting in this direction, and let us call that friction value as our F. Force due to friction, that is F of F. And from here we can use our Newton's second law and the tangential direction. So therefore we can write that our total tangential force will be equal to the mass and multiply by tangential acceleration. Tangential acceleration. And the total force, we can write this as our f of f minus mg sine of mu is equal to m into a. And let us call this equation number 1. And there is a rolling without slipping, so obviously torque will be also into the picture. So let us calculate the torque equation about the ball's center. Torque equation about center of the ball. Now here, one force is the frictional force and other one is our mg, that's the weight, and the gravity that mg is acting through the center of the ball. Okay. So there will be no torque because of that mg. Okay. And the torque will be only because of now the frictional force. Therefore, we can write that torque due to friction, and we have our lever arm, that is our radius r, and the frictional force is our f of f, and this comes as a negative. Okay, because we have taken that the clockwise is going to act as a positive direction. In this case, it is acting in the counterclockwise. Okay, that's why we have taken this as a negative. And from here, we can easily write the rotational equation. You can say rotational equation, and that gives us minus r is equal to our moment of inertia, and alpha is our angular acceleration. And we know that for solid sphere, the moment of inertia is 2 by 5 mass into radius square. Now we can use the condition, which is the no slip condition, and solve it further. So we have no slipping, so it means our acceleration A will be equal to our r multiplied by the angular acceleration, that is our alpha. And we can substitute this equation, and from here we can write that as our minus r f of f is equal to moment of inertia, we already know, is about 2 by 5 mr square, and we can, okay, for the time being, let's keep our alpha as it is. We can just sort out that later. And this radius goes by the square, and okay, let's substitute it and solve it here only. And we can write that our alpha will be equal to a upon r, and this r further cancel out by our r. Therefore, from here we can write that minus f of f will be equal to 2 by 5 mass into acceleration. And now we can substitute our original force equation, and that is our equation number 1. Okay. So you can say from equation 1, we can write, let me once again write this as f of f is equal to mg sine of mu is equal to mass into acceleration. This is our equation 1, and in this equation we can substitute easily our value of our friction, so we can just put minus on the other side. So we get this as minus 2 upon 5 mass into acceleration minus, and we have our mg sine of mu is equal to ma, and this mass cancels out throughout, and we can combine our acceleration term. So from here we can write that our g sine of mu, and this will be coming as plus 7 by 5 times a is equal to 0. Okay, now it is a simple calculation. Okay, in this case we have to remember that we are given that the angle is very small, therefore we can say that a small angle approximation sine of mu is approximately equal to mu. Okay. Therefore we get that g of mu plus 7 over 5a is equal to 0. Okay. And like we said at the start also, that the center of this ball is going to move in the radius of r minus small r. You can say that our center of ball moves in the circle of radius r minus small r. Therefore we can write that our acceleration a will be equal to r minus small r and double derivative of our angle. And this r minus small r, because this small r is very much less than this capital R, so this can be approximately written as our r times double derivative of our angle. And let us call this equation as equation number 2. So in this equation we are going to substitute value of our a. So from equation 2, we get g of mu plus 7.5 r mu double derivative is equal to 0. Okay, now it is almost done, and we can just write it in the standard form of equation of our SHM, which gives us the double derivative of our angle plus, and we get this as 5 times 5 by 7 basically, and we have this as our g upon r mu double derivative is equal to 0, and this is our standard equation of our SHM. So we can make a comparison with our x double derivative plus omega square x is equal to 0. Therefore we can say that our omega is equal to 5g upon 7r and its square root. Or in terms of our f, we can write our f is equal to 1 upon 2 pi square root of 5g upon 7r. This is the frequency of oscillation of our this smaller ball inside the cylinder. And in the next question we are going to do a little variation of this same question, So in the next question, it states that a hollow cylinder of mass m1, radius r1 rolls without slipping inside a large hollow cylinder of mass m2 and a radius r2. The larger cylinder can freely rotate about its axis. The smaller cylinder stays near the bottom and makes a small oscillations. Assume the smaller one is much smaller, that is r1 is very much less than r2. What is the frequency of these small oscillations? So the major difference between the first question and this question is that in this question the larger cylinder is also free to rotate about its axis. In the first question the larger cylinder was fixed. So this is the major difference between the two. And so first of all, let us write the equation for their respective moment of inertia, because in this case both the larger as well as the smaller cylinder are going to rotate. Okay. So we start with our smaller cylinder. So we can say for small cylinder, mass is given as m1, radius is of r1. Therefore, we can write its moment of inertia is equal to our m1 r1 square. And for our large cylinder, we can write that our I2 is equal to our m2 r2 square. And in the question it is also given that the radius of this r1, that is smaller cylinder, is very much less than our r2. So we have to keep this in mind. And so in this case, let us write the torque equation for each cylinder, because both the cylinders will be rotating. Okay, and there is no slipping, only you can say rotation is there. Okay, so let us first of all write the torque equation for small cylinder. Torque equation for small cylinder and so we have a, okay, so there will be a tangential force, and let us call that tangential force will be a frictional force, that is our F. So you can say for small cylinder, for a tangential force F, for tangential force, which will be nothing but our frictional force, or a tangential force or frictional force F, we can write that our tau 1 will be equal to F times R1. Okay. And moment of inertia we already know, so let me write it again. I1 is equal to m1 r1 square. And so in this case, we assume we have to consider three different angles. Okay, so let's define the angle, particularly for this smaller one. So we can say that Now the smaller one is going to have two angle associated with it. First will be its own spin angle, and other one will be because of the orbital position of the small cylinder. So there will be two angle that will be associated with this small cylinder. And so for that, let us say that we are having angle is mu1, and this angle we can call it as a spin of the small cylinder. This is due to spin of small cylinder. And the second angle that will be associated with this small cylinder, let us call this as mu, and this mu will be because of the orbital position of the small cylinder. Orbital position of small cylinder. Okay, so there will be two angles that will be associated with this small cylinder, and therefore we can write that the angular acceleration of the small cylinder will be equal to its spin angle, that is mu1, and its double derivative. And therefore we can write that our F times R1 will be equal to over I1 times mu1 double derivative. We can substitute value of our I1, that is moment of inertia, and we get this as m1 R1 square mu1 double derivative. And we can cancel out, this square factor, and this gives us that our F will be equal to, and we have this as our m1 R1 mu1 double derivative. And same analysis we are going to do for our large cylinder. So we can say for large cylinder, and because the smaller cylinder is going to push the larger cylinder in the opposite direction, so obviously the torque sign is going to be reversed. Okay. Therefore we can write that small cylinder pushes it in opposite direction. Therefore we can write the equation that our F times our R2 will be equal to negative of our I2 and its angular mu2. Okay. And mu2 is our spin of larger cylinder. Okay. That is our mu2 is our angle, is our mu2, and this is due to spin of large cylinder. And therefore we can say that our so we can substitute value of our I2, and this gives us F times R2 is equal to minus m2 r2 square and mu2 double derivative, and we can cancel out this r2, which gives us that our f is equal to our minus m2 r2 and double derivative of our mu2. Now we can use our no slipping constraint. So we can say no slipping constraint. Now in this case we have to remember that all the we have two cylinders and we are having three types of motion that are associated with it. Okay. The internal cylinder, that is a smaller one, is having two types of motion. Both, one is the angular displacement and other one is because of the spin moment, and the outer there is only spin moment is there. Therefore we can say that this no slipping constraint, it is basically going to give us the relationship between our mu1 and mu2. We are going to find out the relationship between these three angles by using the no slipping constraint. And we have to remember that the smaller cylinder is inside the bigger one and it is rolling. Okay. So which basically means that our big cylinder rotates, and because of this rotation moves, the contact point is also moved. So we can say which moves the contact point. And the second one is our small cylinder rotates, and this is, we can say, it rotates because it adjusts because of the because of our rolling. So we can say adjusting for rolling. And finally we have our the center of small cylinder moves along the circular surface of at angle of mu. So we have the center of small cylinder moves along the circular inside surface, along the circular inside surface, and we are already knowing that this angle is given as mu. We have taken it mu rather, but we know that for no slipping condition the linear velocity of the contact point must be equal to 0. So we can write that linear velocity of contact point must be equal to 0. So in terms of equation, we can write this at the velocity of our big cylinder surface, velocity of big cylinder surface minus velocity of small cylinder surface, velocity of small cylinder surface minus, and finally will be our motion of the center. Motion of center should be equal to 0. So this is the basic condition it has to follow about that the linear velocity of the contact point should be equal to 0. And we can write based on the angular position and the radius that is given to us. Therefore we can write from here that our R2 and its angular is velocity will be first derivative should be equal to our R2, and our mu2 its first derivative minus R1 and mu1 its first derivative. Okay. And in terms of angular also we can write it, we can simply integrate it, and we can write this as our R2 mu will be equal to R2 mu2 minus R1 mu1. Okay. So this is the basic constraint equation which gives a relationship between the angular mu1, mu2 and mu1. And next we can also, if we differentiate it twice, we can get the relationship in terms of our acceleration also. So we can write this as R2 double derivative is equal to R2 mu2 double derivative minus R1 mu1 double derivative. Okay, so this is our also the equation in terms of our acceleration by, you can say, double differentiation. And we are going to eliminate from here two angular positions. First we are going to eliminate our mu1 and double derivative, that's the angular acceleration associated with this mu1, and second we are going to eliminate our mu2 double derivative. And we already know the relationship that our F times R1 is equal to m1 R1 square and mu1 double derivative. Therefore from here we can say mu1 double derivative is equal to F upon, okay, so we can just cancel it out, and this gets m1 R1. And similarly we can write that our mu2 double derivative will be equal to minus F upon m2 R2. And we can easily substitute in this equation. Let us call this as equation number 1. So we can say from equation 1, we get this as our R2 mu double derivative is equal to R2 minus F upon m2 R2 minus R1 F upon m1 R1. And here we can just cancel out our R1 R1 R2 R2, and this gives us that our, we can write this as our to mu double derivative is equal to, we can take minus of f as common, and this will be coming as 1 upon m1 plus 1 upon m2. And we can just shift the negative sign to the other side. So we can write this as f upon 1 upon m1 plus 1 upon m2 is equal to minus r2 mu double derivative. We are going to use this particular equation later on also. And now we come to our smaller cylinder and find out the various forces that will be acting on it. So you can say that force balance on small cylinder. So we have assumed that our, suppose this is our bigger cylinder, and inside we have our, suppose this is our mean position, and we assume that our, this smaller cylinder is somewhere here, and it is making angle of mu with the its lowest position, or we can say the vertical. And forces that will be acting will be over mg. We can divide that mg into two components. This will be also angle mu, so we have our mg sine of mu, and we have this as mg cos of mu. And there will be also, because it is, there is a slipping, there is no slipping condition, so there will be friction force, let us suppose that is of F. And therefore we can write that so we can write the equation for the motion, and we can say from Newton's second law, which gives us F minus m1g sine of mu is equal to, we have our this tangential acceleration, and we can write this as our m1 r2 mu double derivative. And okay, more or less things are done now. We are going to simply solve it now. And let us call this as equation number, this is equation number 2 and this is equation number 3. Therefore we can say that our we have F okay, so let me write the equation number 2 first of all, then we can come to its solution. So you can say from equation 2 I can write my force F will be equal to minus R2 mu double derivative, and this comes as 1 upon our m1 plus 1 upon our m2. Okay, and we can take our LCM, so we get F is equal to minus R2 double derivative, and this gives us m1 m2 will be our, and this comes as our m1 plus m2. Now we can just substitute in equation 3 the value of our f. So you can say from equation 3 we get this as our minus r2 mu double derivative m1 m2 divided by m1 plus m2 minus m1 g sine of mu is equal to, and we have this as our m1 r2 mu double derivative, and we can cancel out our m1 throughout. And what else? Okay, we can keep rest of terms, and we can just collect or group the same terms, and we have our r2 mu and r2 mu on the other side also. Therefore we can write this as our minus r2 mu double derivative, and we get this as our m2 m1 plus m2 and plus 1 is equal to, we can write this as our, we keep it as it is because we want this as a equation of our SHM. So minus g sine of mu is equal to 0, and we can take m1 plus m2, okay, we can take this as LCM, and we can remove this as a negative sign. Therefore we get that our r2 mu double derivative will be equal to, we get this as m1 plus m2, and this will be equal to m1 plus twice m2 plus g. Okay, we can use our small angle approximation, and our sine of mu will be approximately equal to mu. So this will be equal to mu, so this comes as mu is equal to 0. And now it is a simple manipulation. We can write this as mu double derivative plus, and we can write this as our g upon r2 times m1 plus m2 divided by m1 plus twice m2 times mu is equal to 0. And this is our equation of our SHM, that is our x double derivative plus omega square x is equal to 0. Therefore we get that our omega will be equal to our g upon r2, and we have this as our m1 plus m2 divided by m1 plus twice m2 and its square root. So this is the angular frequency of our smaller ball. Okay, so we did two questions. The only difference between the first and second question is that in the second question the outer or a bigger cylinder was also rotating. Okay, this is the major difference between these two questions. And we come to our third question, and in this third question we are given that three identical cylinders, each of moment of inertia I is equal to half mr square, are arranged in triangle stack as in the figure. I'll draw later on. One cylinder on the top and two on the bottom, and we are given that find the initial downward acceleration of the top cylinder in each of the cases. So we have to find out the acceleration of each of the top cylinder in two cases. First case is the bottom cylinder rolls without slipping on the ground, there is a friction between with the ground, but there is no friction between any of the cylinders. Part 2, there is no friction with the ground, but there is a friction between the cylinder, so they do not slip against each other. And we are also supposed to do, finally, determine which case gives the larger downward acceleration of the top cylinder. And so let me draw the basic figure. So we are given two cylinders, three rather, two on the bottom, and they are stacked close to each other, and the third one is lying in between them, something like this. So this is the basic figure given to us, and this is the basic platform on which, horizontal surface on which they are lying, and each cylinder is having a radius r and mass is m. Okay. So we have all these three cylinders will be having the mass of m, and in this case we have to remember that in the first case there is a friction, and the second case there is no friction between the cylinders. And in the first part it states that the bottom cylinder rolls without slipping, so there is only friction between the bottom cylinder, and let us call these centers as C1, C2 and C3. And these, if we join the centers of these three cylinders, we are going to get an equilateral triangle of each side will be equal to 2r. Okay. And obviously the angle will be equal to 60 degree. Okay. And so, okay, and the forces that will be acting on the bottom two cylinders, because one will be frictional force, because the friction exists between C2, C3 and the ground. Okay. And there will be also normal, because between the C1 as well as C2. So it means let's calculate for one cylinder, and that we can replicate for the second cylinder also. So let us consider the rightmost cylinder, that is C3. So we can say for cylinder C3 we are having horizontal frictional force let us call that as F, and we are also going to have a normal force that is of N from the top cylinder, from the top cylinder. So these are the two forces that will be acting on this. Obviously there will be a weight, that is mg, that is going to pass through the center. Okay. And if we look closely, we can see that the normal is also going to pass through the center of this sphere. So this is value of normal, and we are going to have a weight mg that will also going to pass through the center C3. Okay. So it means only the horizontal frictional force F is going to produce the torque at the bottom cylinder C3, and that will be the same condition for C2 also. And so we can say that, so let's define the acceleration. So we can say that we are okay. So everything will be discussed with respect to the bottom right cylinder, that is our C3. can say for C3 we assume that the horizontal acceleration is suppose A of x, and for our cylinder C1 there will be a vertical acceleration for C1 we are having vertical acceleration which will be in the downward direction, and that is our A of y, and horizontal acceleration A of x on C3 will be towards our right side, and A of y will be in downward direction, and we are going to take this as A of y as positive. Downward we have taken it as positive. Okay. So it means that our C3 is moving in the downward direction with the acceleration of A of y, and we have our, not C3, sorry, this is C1, and our C3 is moving towards the right with the horizontal acceleration of A of x. And so we can divide or write the equation for our forces for respect to cylinder C3. So we can say that forces on C3, and we have a normal on C3, okay, and this we can divide into two components, and we know that its angle is, this angle is about 60 degree, so we can divide this into two components. So this will be also over 60, so we get this as n cos of 60, and we have this n sine of 60. Therefore we can write that our n of x, that is in x direction, so we can say our n of x will be equal to n cos of 60, and our frictional force will be in the opposite direction, that is in this direction, so this is our frictional force F. So we can write the equation for our motion, so we can say Newton's second law, this gives us n cos of 60 minus F will be equal to mass into acceleration, which we have stated as A of x. And so this is our one of the equation. Similarly, we can consider for our top cylinder, that is a C1. So we can say for C1, and so for C1 we are going to have this will be our normal, and we can divide, so this is our horizontal, and we get this will be our angle of 60, and can divide into two components, this will be our n sine of 60, and we get this n cos of 60, okay. And there will be a weight mg, so this is our center, that is our C1, and it will be acting in downward direction, that is our mg, and this was our C1. You can say that our vertical component. Is equal to n sine of 60. So we have two cylinders, C1 and C2, and therefore there were total upward force. So we have total upward force will be equal to, this will be twice n sine of 60, because we have two cylinders which are pushing. So one contact force will be because of our C2, another contact force will be because of our C3. So therefore the total vertical component will be, one will be of C2 and other one will be of C3, and the magnitude will be same in both cases. So this is a total upward force, and the weight that will be acting in the downward direction will be our mg, that is our C1. So we have our Newton's second law. We can write that mg minus twice n sine of 60 will be equal to m a of y, and this is our, let us call this our first equation, and this is our second equation. And now we come to the torque part, because there is a friction that is acting on the two cylinders which are in contact with the ground. So the total forces on C2 or C3 will be frictional force, the weight as well as normal. The weight and the normal will be passing through the center, so it won't be producing any torque. The torque will be only because of the frictional force. Therefore we can say for our C3, so we can say for C3 we can write that our friction is only force producing torque, about center, because the normal as well as mg are passing through the center. Therefore we can write that the torque will be equal to force multiplied by the lever arm, that is our R, and the moment of inertia we can generalize the formula I is equal to our beta mr square, moment of inertia of our cylinder. And for rolling no slipping condition we can write that the angular acceleration will be equal to our linear divided by r. Therefore we can write that in substituting this equation we can say that our Fr is equal to our moment of inertia, that is our beta m r square times a of x upon r, and here this r cancels out throughout, and this gives us that the value of f will be equal to, we have this as beta m times a of x. Now we can also find out, or rather we can say we need to find out the relationship between both acceleration, that is a of x, as well as our a of y. Okay. And for the ease of that, so let us relation between a of x and a of y. And for that, let us draw a coordinate system, much more convenient using the coordinate system. And we have the bottom cylinder is having initially at our C3, and the top cylinder is at our C1, and the coordinate are r comma 0, and its coordinate is our 0 comma square root of 3 times r, that is the height of the center, because that is basically our triangle. And the distance between the center is obviously our 2r. Therefore, we can say that our C1, its coordinate is given as 0 comma square root of 3r, and we have a C3, its coordinate is our r comma 0, and we assume that our C3 moves towards right side through a distance of x, and C1 moves downward through a distance of y. Okay. Therefore, we can write the new coordinate of our C1 prime, and that will be equal to our 0 comma root 3 minus of y, and we can write our C3 prime will be equal to, we get this as our r plus x comma 0. But the distance between this C1 and C3 will be always equal to 2r. This distance is not going to change. And so we can write the equation as our r plus x minus 0 whole square plus 0 minus square root of 3r minus y whole square is equal to 2r whole square. And we have to keep in mind this value of our x as well as y is very small. Okay, this distance which these are moved is comparatively small, and therefore we just open the bracket and sort it out. We can write this as our r square plus 2rx plus x square, and this comes as plus 3r square minus twice square root of 3ry, and plus y square is equal to 4r square. And like I said, that the value of this x and y is very small, so obviously x square and y square we can neglect it, and this r square will be 4r square, and this goes by 4r square. And furthermore, we can just, okay, let me write it here, 2rx minus 2 root 3r y is equal to 0. So obviously value of this 2 cannot be equal to 0, and this r we can just remove, that is value of r cannot be equal to 0. Therefore, from here we can say that our x is equal to square root of 3 times y, and if you double derivative it, we can get that the acceleration in x direction will be equal to square root of acceleration y direction. So this is the relationship between our acceleration of our this C cylinder as well as our C1 cylinder, or we can say this is a constraint relationship between the acceleration. Now we are having 4 equations. Let me write it down. So first equation is our n cos of 60 minus f is equal to m times a of x. Next is our mg minus twice n sine of 60 is equal to m a of y, and other one is our f is equal to beta max, and finally is our a of x is equal to square root of 3 a of y. And we need to solve all these 3 simultaneous equations to get our answer, because we have 4 equations and we are having 4 unknowns. The unknowns are the normal, the force, and the 2 accelerations. 4 unknown, 4 equations, and so that's the only solution part. I'm going to just skip it and provide the final answer. So we get our acceleration of our y, that is the downward acceleration of our cylinder, top cylinder, will be equal to, this comes as g7 plus 6 times beta. So this is the downward acceleration of our top cylinder. Okay. Now we come to our part B. In part B, the only thing that changes is our friction. Rest is going to our same. Therefore, we say that our part B, the arrangement of the cylinder is same, and the only is the relationship is our a of x is equal to square root of 3 a of y. Okay, this relationship is obviously not going to change, and now we are given that there is a frictional force between the cylinders. Okay, so we have to keep that in mind. So let us consider our bottom cylinder, and now the bottom cylinder is going to have now 2 forces, rather we can say 3 forces. One will be friction, normal, as well as mg. Okay, so we are interested in friction as well as the normal. So we can say for our cylinder C3, and we can just, so this is a C3 and C3, and we are having a normal force N, and we can divide into 2 components. So we have our, this will be over 60, so we have N cos of 60, and we have this as N sine of 60. Okay. And we are going to have a frictional force. So this is a frictional force F. So we can divide this also into 2 components. So we get, this will be over angle 60. So we have our F cos 60, and we have our F sin 60. Okay. And like you said, that C3 is moving towards the right with the acceleration of our AX. Therefore, we can write from Newton's second law, we can write the equation of motion. And that equation of motion will be equal to our N cos of 60 minus F, sorry, one second, my mistake, this angle is not 60, this angle is 60. So we get this as F cos here and sine here. So we have F sine of 60 is equal to m times ax. Okay. And this was our for C3, the bottom cylinder. Okay. Bottom cylinder. Now we come to cylinder C1, that is our top cylinder. So you can say for C1, that is our top cylinder, and so this is our top cylinder, and we have this is our C1, and there will be normal force, that is a contact force, and the frictional force will be obviously in the opposite direction. So this will be our force F, and we can divide, because we are only interested in the vertical part, we can divide this into two components. Okay. So we get this as our, this will be n cos of 60 and n sine of 60, n sine of 60, and this will be n cos of 60, and we are having our f, so we get this as our f cos of 60, and this will be f sine of 60. Okay, and this C1 is only moving in downward direction with the acceleration of our a of y, and this C1 is having the two contact surfaces. One is because of C3, and the same will be because of C2, okay, because it is stacked like this. So it is going to have two contact forces. Okay, so from the other end we are also going to have two forces. Okay, so there will be, on the other end we are also going to have our n sine of 60, and other one will be f cos of 60, and there will be a weight mg acting downward. Therefore we can write the equation as, you can say, equation of motion we can say that our mg minus twice n sine of 60 minus twice f cos of 60 will be equal to mass into acceleration a of y. So we got the equation of our this according to our second law. Now there is also a frictional force between the cylinders, that is C1 is having a frictional force, this is our C1, C3, and this is our C2. So there is a frictional force between C1 and C2, and there is a frictional force between C1 and C3. So obviously you can write the torque equation, because it is said there is a rotating without slipping. So you can say that for C3 we can say that the torque tau is equal to F times R, because this torque will be because of the frictional force Fr, and we can further write it as our moment of inertia in terms of moment of inertia, and we can say our Fr is equal to, let us put this as our alpha, beta, gamma. So let us put this as gamma mr square times angular acceleration alpha. And gamma is a variable, and that varies according to our cylinder, whether it is a hollow cylinder or solid cylinder. And now we have to find out the relationship between our linear acceleration a of x as well as the angular acceleration alpha. So we can say relation between alpha and a of x. And because there is no friction between the bottom cylinder, that is C3, and ground for the second part, so obviously the bottom cylinder is going to slip. Okay, therefore we cannot use the basic relationship. Okay. And like we calculated in our first part, I'm straightforward going to write the equation. So we can say that our delta theta will be equal to twice d square root of 3 times r. Okay. And from here, if we derive it, we can get that our alpha is equal to 2 by square root of 3, and this distance d comes our a of x, and divided by r. Here d, we assume that the bottom cylinder C3, this is our C3, it moves through a distance of d. And so this gives a relationship between our alpha as well as our a of x. Okay. Once again, we have 5 equations and 5 unknowns. Okay. And if we solve them, we can get the answer. So I'm going to straightforward write the answer. So we have our a of y will be equal to g7 plus 8 times gamma. So this is our acceleration of our of the top cylinder whenever there is a friction force between the two. So this completes all the 3 questions from today's session. So we have to keep in mind that this specifically for this second part, I've skipped entire calculation because it is lengthy, but all the equations have been derived. So based on this, so this completes all the 3 questions.